Let's talk about friction, a messy, sticky subject. All right, so friction is a resisting force and it will always opposes the direction of motion if there is motion. Of course, the velocity is not zero. Or balances forces if velocity is zero. If you've got a static situation, in other words, the word static means things are not changing, so that would be a situation where you have no motion. Right? Static means not moving. So we have two kinds of friction. We have kinetic friction and we have static friction, these two situations here. And in either case, our mathematical model, in other words, equation for friction, is that the amount of friction you have is directly proportional to the normal force. So we're going to write that like lowercase f for friction. That's the, let's say, force of friction is, I'm going to leave this blank for a second here. It's directly proportional to some coefficient of friction. This is the coefficient of friction, more about that in a second, times the normal force. Now I left this blank. If you're wondering why didn't I just write an equal sign there, we're going to write it like this. If we want to just write one equation to capture everything about friction, we'll write it like this, because when you have static friction, there's only enough friction to keep things balanced, or as much as is necessary to keep things balanced, up to a certain point where that friction breaks, and then you get motion. So kind of like a normal force. The desk that I have all my stuff set up on right now, this desk could support more than what it's supporting my little recording studio here. It's supporting that, but it could support more. For example, if I take my hand and I push down on this, then there's more normal force pushing up. And if I release my hand, now there's less normal force pushing up. And there's as much normal force as there needs to be to support it, whether I'm pushing down on it or not, up to the point where the whole table would collapse because it can no longer provide that amount of support. Of course, I can't push down that hard. Not going to try. So friction is, static friction is the same in that we have, if I push on this calculator, I can push kind of softly, and like I am applying a little bit of force with my pen here, but not enough to break that friction force. So I can push a tiny, tiny bit. There's a little tiny bit of friction there, and then a little bit more until I break that static friction. So there's as much as there needs to be to keep it still up until it can't get it done anymore, and then you have kinetic friction. Then things start moving. Okay, so this kind of captures both of those. For static friction, which we can write F with a little subscript there, static friction is less than or equal to some coefficient of static friction times the normal force, and kinetic friction is equal to the coefficient of kinetic friction times the normal force. So you note here that this is an equal sign here. If you have kinetic friction, once you have motion, then there's no like, how much is there? Well, it depends. Once it's moving, you have a certain amount of kinetic friction, and that's that. But when you have static friction, there's only as much as there needs to be to balance the forces, just like with the normal force. What about these coefficients? What do coefficients of friction tend to look like? So these almost always a number, and it has no units. Why would it have no units? Well, if you look at the equations we have here, or inequalities that we have here, this is a force and this is a force. So for this to be dimensionally consistent, this is doesn't have any units. Or, if you prefer, it has units of newtons over newtons, like newtons per newton. How much friction do you get? Well, you get like half a newton per newton of normal force. So you can think of it that way, or you can think of it as just being like a scale factor. But it doesn't have any units, which is unusual for us. So it's a number with no units, or newtons over newtons, if you prefer. That is between 0 and 1. And if you think about that for a second, why would it be between 0 and 1? Well, how much friction are you going to get? You're going to get typically some percentage of how much normal force you have. But it would be weird if the amount of friction, if you imagine something sitting on a flat surface, if the amount of friction, like opposing motion, let's say, could be more than the weight of the object. If you have something on a flat surface, then it's in the absence of any pulling up or pushing down on it, its normal force is just going to balance its weight. Its normal force is just going to be equal to mass times 9.8 newtons per kilogram. So it would be really, really weird if it could resist, if you were pushing on it sideways and there was so much friction that even if you pushed with a force equal to the weight of the object, it still didn't budge. All right, so imagine like a big cardboard box with like a washing machine in it or something like that, and you're trying to push that across a linoleum floor. So how much force are you going to need to push that? Well, it's going to take a lot of force, but it shouldn't take more force to get it moving sideways and overcome friction than it would to just lift it up, right? So it's possible to engineer special kinds of situations where there is more friction than that weight, but it's pretty unusual. So we're going to be seeing numbers between 0 and 1, and usually the coefficient of kinetic friction is less than, or sometimes might be equal to, but it's typically less than the coefficient of static friction. You've experienced this before, so imagine that same like very heavy cardboard box. You've experienced this where you're pushing, and finally it like breaks free, and it's like it becomes unstuck. And then once you get it moving, it seems like it's a little bit easier to get it moving again. And then if you like stop for a second, it kind of like sticks again, and then to get it moving it takes a little bit more, and then once you get it moving, as long as you keep it moving, it seems like it takes a little bit less force. So that's because that kinetic coefficient is usually less than. We could go into like the sort of microscopic level, like what's going on there, the sort of there's intermolecular things going on. There's a reason that that happens, but it's really kind of at a level of detail that we're not interested in here. So I'm not going to go into that. I think there's a little bit maybe in your book about that, so you can check that out if you're interested. All right, so that is what we need to know. And I think from here, now that we have these mathematical models, I would like to just go ahead and jump into doing a few example problems. 2, 10, and 12 I think I'm going to do from your book, and give you a feel for what it's like to do problems with friction. All right, so number 2, we'll just continue here at the bottom of this page. In a pickup game of dorm shuffleboard, students crazed by final exams use a broom to propel a calculus book along the dorm hallway. If the book is 3.5 kilograms, and it's pushed from rest through a distance of 0.9 meters. So from rest, it's pushed through a distance of 0.9 meters, and there's a horizontal force of, that's the pushing force, of 25 newtons. And then it has a speed of 1.6 meters per second. Then what's the coefficient of kinetic friction between the book and the floor? Okay, so there's a lot of information here to process, but I know for sure I'm going to need to make a force diagram. So there's no ramp or slanted business going on here, so that means my axes along which I will put the forces are just going to be regular old horizontal vertical. So I'm going to have a gravitational force of 3.5 G. Grabbed the wrong number there. 3.5 G. And the normal force, there's no motion in this direction for sure. So that normal force, which is going to be important now. In Chapter 5, we put lots of normal forces into force diagrams, but we never really did anything with them. And we're going to need them now because the force of friction depends on how much normal force there is. And I guess I didn't say anything about that. That should make sense to us that it depends on the normal force, because a normal force is like a measurement of how much two surfaces are pushing against each other. So, you know, how much resistance is there? Well, how hard are they pushing together? So that's that. And then I've got this pushing force of 25 newtons. And then I've got friction force. And I don't know what this is, but I know it's definitely less than this because it is getting accelerated from 0 to 1.6. So definitely this is winning. And anytime you make a force diagram, well, not every time, but most of the time, I think we want to make a Newton's second law equation for this. Sum of all forces is equal to mass times acceleration. So these are balanced, and then winner minus loser here. So I would have that pushing force minus the force of friction is equal to mass times acceleration. I think I'll leave that like that for now. So if we look at this and think about what we would like to find, I think that we are looking for what's the coefficient of friction. Well, here, kinetic friction is equal to the kinetic coefficient times the normal force. And in this case, the normal force is equal to 3.5 G. So I've got mu, that's what Greek letter that is, mu times 3.5 times G. So I can replace this friction force with that. So this is the thing that I'm trying to find. I need to get that into my equation. Let's go ahead and do that. Let's put in everything that we know at this point. So the force of the push, 25 newtons. I'm going to leave my units out to keep the equation a little cleaner for solving purposes. Minus, and then I've got 3.5 G. Let me go ahead and get a number on that. 3.5 times 9.8 is 34.3 times that kinetic coefficient that we're interested in finding, is equal to the mass of the book times its acceleration. Well, I can't have two unknowns in this equation, so I'm looking back over here, and if I know this initial velocity, final velocity, and the delta x, then I can do a little kinematics. right? Find that A. So 1.6 squared is equal to 0 squared 2 times A is 0.9. So I'm going to do some math. Oops. Typed in 106 instead of 1.6. It's not the right answer. What are we doing? 2 sig figs here, so 1.4 meters per second squared. That's my acceleration. And now I can solve for that coefficient. And remember, before I do anything else, I'm expecting a number between 0 and 1. Kinetic coefficients are often like somewhere in the 0.2 to 0.4 range, something like that. Let's see what this one comes out to be. So more math. Ooh, that's kind of high. 0.59 I got there. And I forgot to do my little printout of the answer key, so I sure hope that that's right. The process is correct anyway, and I'll check afterwards and I'll make a note just in case there's any mistake, but we'll just presume that that's correct. So that's how we do that. And you can see that we really have some elements of a lot of the things that we have done so far this year. We have our kinematics, we've got our nice force diagram, Newton's second law, and we're just introducing one new thing that now we can quantify this frictional force using these mathematical models here. It just depends on that normal force. All right, let's do another couple examples. How do you know whether you're supposed to do the kinetic or static friction? Well, if it's moving, you do kinetic friction, and if it's not, you do static friction. But sometimes you don't know. I think that's going to come into play in this problem. Number 10. Sometimes you have to figure out if it would be moving or not. So we got a classic, physics classic here. The old force pulling on something. I mean, this happens, right? So situation like this, and what are the details? We've got something that has a mass, they're not going to tell us, it just has a mass of m. And then the pulling force is 0.5 mg. And the angle's 20 degrees. What's the magnitude of the acceleration of the block across the floor if the friction coefficients are, for part A, 0.6 and 0.5, and then for B, well, we'll do that in a minute. Okay, so before we do anything else, let's just make a force diagram. So here, my dotted lines are going to be regular old axes like this. I'm going to have my force of gravity, which is mg, and I've got this pulling force here, which is half an mg. Sorry, this is not drawn to scale. And I put in my components with dotted lines. Always those have to be dotted lines. You can't add them in like they're other forces. They're the parts of this one. So let's see, 0.5 times the cosine of 20. That's going to be 0.47 mg. And then 0.5 times sine, that's going to be 0.25 mg. Right? Now, how much normal force is there? That's important for us. There's not this much normal force because there's a little extra helping here in the up direction. So I need the ups and the downs to balance. So if this is mg down and I've already got a quarter of an mg up, then that normal force only needs to be 0.75 mg. And if you think about this, like mapping this onto the real world, what's actually going on, if you're pulling slightly upward on this box, then if you had a scale underneath this, it would, in fact, the reading would go down, right? There would be less upward pushing force. All right, so we have balance now in the up-down direction. These two in the up direction balance this in the down direction. Now, how much friction? That's the question. So now that we've got that set up, how much friction is there going to be? Well, there might be this much. If the static friction coefficient allows us to have this much friction, then it will be static. But if this forward horizontal force exceeds the maximum amount of static friction that we could have, then we have to say, okay, it's going to be moving, and then we would figure out how much kinetic friction there would be. So we have to check the static condition first. And we could set that up, we could think about it like this. The static frictional force, the maximum that it could be, would be if we just set it equal to this. Now, this isn't saying there will be this much. This is just what the maximum could be, how hard you could push in this direction on this box or block or whatever it is without budging it. So the maximum amount of static friction that there can be is the static coefficient times the normal force. So 0.6 times 0.75 is 0.45 mg. That is the maximum. Oops, oh yeah, that's right. I'm sorry. That is the correct calculation. So that is 0.45 mg. That is the maximum amount of static friction that there can be. So what does that mean? It means since there is this much force in the forward direction, this cannot get it done. It cannot balance this. Not enough. So that means we don't have a static situation. We have a kinetic situation. So the velocity is not equal to 0. And that means that we have kinetic friction. How much? Well, the kinetic coefficient is 0.5 times the normal force, which is 0.75. And that gives me 0.38 mg. And what are we doing? Are we finding the acceleration? Yes. So now that we know that it's this, we could say in part A here, the sum of all forces, is mass times acceleration, that would be this minus the friction force is equal to mass times acceleration. And look, there's a mass in all of those terms, so that cancels out, and I get that the acceleration is equal to 0.09 times, so 0.88. All right. Part B, there is a smaller static coefficient, so that is going to mean that definitely if this can't get it done, then a static coefficient of 0.4 definitely can't get it done either. So I'm going to leave that for you. That's enough of an example, I think. And then 12, we've got this guy who is just ridiculously strong, or his hands are anyway, Henry Sinkowski of Philly. And he's gripping, you see the picture in your book there, I don't need to describe it to you. And his mass is 79 kilograms. If the coefficient of static friction between the hand and the rafter was 0.7, what was the least magnitude of the normal force on the rafter from each thumb or opposite fingers? Let's make a force diagram here. What's going on? So he does have two arms, as you can clearly see in the picture. So the force of friction here we've got on him. There's a force of friction on each thumb. This is not exactly a traditional force diagram here. So this is like one hand here. That's his fingers and his thumb, and this is his thumb and his fingers on the other hand. Those are all frictional forces upward. And then downward on him, there's the gravitational force, mg. So each one of these points of contact, there is a frictional force at each one of those. So each one of those must be equal to, there's 4 of those in the up direction and this in the down direction. So each one of those must be equal to mg over 4. And we're talking about static friction here, right? So they say, like, what is the least magnitude of the normal force if the static coefficient is 0.7? So if we're at that maxed out condition, then we can use this, right? So let's see, that is going to be equal to this frictional force is going to be mg over 4 is equal to the static coefficient is 0.7, and then times the normal force. That's what we're looking for, right? That's how hard he has to squeeze. So that's going to be, let's see, his mass, 79 times 9.8 divided by 4, and then I'm going to divide that by 0.7. That's about 277 newtons. If you would like to have like just a ballpark way of understanding how much a newton is, we think about force in terms of pounds because we weigh ourselves in pounds and we measure other things, like things you get at the deli at Kroger or whatever. We measure those things in pounds too, like a quarter pound of and so on. So what's this in pounds? The conversion factor is, if you divide this by 5, that gives you a pretty good ballpark. It's actually about like 4.54 or something like that, the conversion from pounds to newtons. But if you divide that by 5, that gives you a pretty good ballpark. So that'd be about 50s, like something in the 50s, right? 50-some pounds of force. Which might be like, oh, big deal, 50 pounds of force. But he's generating that like by squeezing like this. So imagine like grabbing a bathroom scale and squeezing it just with your hand to get it to read 50-some pounds. That is not easy to do. All right. So there's some examples for you. And try the problems, the first assignment 1 through 9 odds. And please try to be efficient about it. Bounce back and forth with the solution videos if you find that style to be helpful. And of course, the answers for the odd numbers are in the back. Good luck with that. Hey, no free pizza again. Got it in under 30 minutes.